Once again, good morning, dear student, and welcome to this third part of our tutorial on conditional expectation and martingales. Finally, we are going to tackle martingale. We are done with conditional expectation in code because martingale in the martingale property of conditional, of the definition of a martingale, we use conditional expectation. So that's why it was good for us to first of all understand how to perform conditional expectation using the different properties like linearity of the conditional expectation, take out what is non-tower properties, and the like. There are many other properties. There are at least 11 properties of the conditional expectation. So we have an exercise here with many questions. The first question, we are given symmetric random variable, as you can see. Psi j is a sequence of IID random variable with common distribution. P, which is the probability of psi I equal to 1, and Q, which is 1 minus P, is the probability that psi I is equal to -1. So here we have a symmetric random variable. No. We're not sure whether it's a symmetric, but actually we have a random walk, a simple random walk. So this is a simple random walk, but it's not necessarily symmetric because for this random walk to be symmetric, P has to be equal to 1/2. If P is equal to 1/2, we have a symmetric random variable. Otherwise, we will just say that it's a simple random variable, which might be unbalanced, right? Okay, so, and Fn is the sigma algebra generated by the psi I. So this is the natural filtration of our random walk, right? So Sn is the position of the random walk. That is, Sn is the sum j running from 1 to n psi j. Obviously, we didn't say it, but if n is equal to 0, Sn will be equal to 0, right? That's by convention, right? So by convention here, S0 is 0. Okay. So by convention, sorry, S0, oh, sorry. Mm. Okay, so as I was saying, we did not specify, but it should be bear in mind that S0 is 0. Good. So the first question is to prove that the sequence of capital M sub n given by the ratio Q by P raised to the Sn is an Fn martingale. And the second question is for a fixed lambda positive, we are asked to determine the constant constant, of course, constant depending on lambda, right? The constant C, which depend on lambda, so that Zn to the lambda, right, which is defined as C to the power of n into lambda to the power of Sn be an Fn martingale. So you can see that things are becoming a bit complicated here. And the second question, we are given a filtered probability space, and we have a sequence Yn of absolutely integrable random variable adapted to the filtration Fn. We assume that there exist real numbers Un and Vn such that the conditional expectation of y sub n plus 1 given Fn is equal to Un into Yn plus Vn. So the question is to find two sequences, An and Bn, such that the sequence of random variable capital M sub n defined as capital N sub n is defined to be An into Yn plus Bn, where n is strictly greater than 1, B, a martingale with respect to the same filtration, Fn. So these are the two problems that we are going to tackle in this video or in this tutorial. So let's start with the first one. Let's start with the first one. To show that in the first problem of a simple random walk, sub n equal to q by p all raised to the power of Sn is an Fn martingale. So that's what we are going to prove. This is easy to do. So we are just going to compute a conditional expectation of M sub n given Fn, where Fn is this sigma algebra generated by the psi j, where j runs from 0 to n. So let's dive into that. So we'll write here a solution. So solution to the first problem, or to the first, to the first problem, or the first question. So as you can see, there are two questions in the first problem, I and double I. So the first one is to prove that Mn given by this is a martingale. So let us copy this question. Okay, so this is what we are proving. So let's dive straight into the solution of this. So what we are going to do, we are just going to compute the conditional expectation. So we are going to prove, or we are going to show that So we are going to show that the conditional expectation of m sub m plus 1 given fn is equal to mn. So if we succeed to prove this, then we are done. So do we have this equality? That's the question. So if that's the case, it has to be the case because we are asked to prove it. We are asked to prove that it is a martingale, so this property has to hold. Obviously, I'm skipping. Remember when we are proving that something is a martingale or a sequence is a martingale, don't forget that there are three properties that we have to prove in total, right? So the first property is that the mn, so for a fixed mn is adapted, meaning that it is an fn is fn measurable. And the second thing to prove, or the second property, is that this is finite, meaning that mn is integrable. Absolutely integrable if you want. Absolutely integrable means that it's integrable. And finally, the last one is the martingale property, which is this one. That is mn satisfy that property, right? Mn satisfies the martingale property, of course, for any n, for a fixed n. So for any n, we have to prove all this. So what we are going to prove, the other ones are obvious. I'm not going to go into that. So I'll go straight to the martingale property. So I'm specifying this so that you will not think that we only prove the martingale property. No, we prove these three properties. So what we are going to prove here is this one, right? This one, the martingale property. Okay, so the procedure is straightforward, right? We are going to compute this straight away using the properties of the psi I, which are RID, and Fn is the sigma algebra generated by the psi j, where j runs from 0 to n. And we'll see that there will be independence in some ways, right? We are going to manipulate all these properties to answer or to solve our problem. Okay, so we start right away. So indeed, indeed, if we write the conditional expectation of this, given Fn, so this is equal to what? We know what our Mn is. Mn, we know that Mn plus 1, we are going to replace it. This will be Q by P to the Sn plus 1 given Fn. But Sn plus 1 written here is Sn plus psi n plus 1. So we can write it here. This will be Sn, because that's the sum from 1 up to n plus 1, from which we can split into 2 and write this. So this is what it will give us. Now, if we raise Q by P to the Sn plus 1, this gives us Q by P to the Sn plus psi n plus 1. And if you use the property of the exponent, right, we can break this into two products. So this will give us Q by P to the Sn into Q by P to the psi n plus 1. And this one, this first factor is Mn. So if you substitute this expression into our conditional expectation here, so this will give us the conditional expectation of what? Of M into Q by P, all raised to the psi n plus 1, given Fn. So that is what this will give us. So I can erase this, since we have already expressed our result in the form that we want at this stage, right? Okay. So, oh, sorry, this is Mn. Okay, now, if you look at at what we wrote above here, that Mn is Fn measurable. Fn measurable. If it is if M sub n is Fn measurable, it means that Mn is none. I can take it out. That is how they take out what is non-property. So I'm going to take this Mn out of the expectation. It becomes like a constant, right? Actually, I mean, we know it, so it's constant. So we can take it out. So then we get M, capital M sub n, conditional expectation of Q by P all to the psi n plus 1, right? Given F sub n. Okay, so now what do we have here? We know that the psi j are independent, right? Psi j is independent of psi I for any I not J. If that is the case, this will imply that if I fix J to be psi n plus 1, this will be independent of psi 0, psi 1 up to psi n. That is everything except psi n plus 1. So if it's independent of this, it will be independent of the sigma algebra generated by all this. So that is psi n plus 1 will be independent of the sigma algebra generated by psi j, where j runs from 0 up to n. And this is nothing else than f sub n, right? Of course, what I've written here can also be written as this. So we can say that psi n plus 1, and then we write this to say independent of f n, which is the sigma algebra generated by psi j, where j runs from 0 to n. So this being said, if this is independent of that, any measurable function or continuous function of this will still be independent of fn, right? Now, if you look at this, this is a function of, actually it's an exponential function of psi n plus 1, right? So this implies that for f measurable or continuous, a continuous function is measurable, that f of psi n plus 1 is still going to be independent of f sub n, right? Okay, so our function here will be an exponential function base q by p. So this is q by p n plus 1. So this is still independent of that. Okay, so I'm going to erase what I've written above there. This is the explanation of the next line that I'm going to write. So with this, I can now write the result that this will be m sub n. So since this is independent of fn, the conditional expectation becomes just the expectation. So this is the expectation of what? Q by p to the psi n plus 1. Right. This is a random variable, so we know the values taken by psi n plus 1, which are, there are only two values, -1 and 1, and we know the corresponding probability, so we can write the actual expression of this, right? We can write this expression. So this will give us mn into, right, or times into that. So now this expression is what? I will substitute the values there. So that will be q by p, the value taken by this random variable when psi n plus 1 is -1. So it will be -1 here times, okay, for -1, if you look at the definition above, when p is -1 is q, and when p is 1, the probability is p. So that's what we are going to write here. So this is Q plus Q by P to the 1, right, times P. So if we rearrange this, we can see that the reciprocal of Q by P will be P by Q. So if you write P by Q here, so this will be M sub n into P by Q times Q plus Q by P into P. Now you see that this P and that P will cancel out. This Q with that Q will cancel out. And it will be P plus Q. So actually this is 1. All that factor is 1, but let's write all the steps. So this will be P plus Q. We know that P plus Q is 1 because Q is 1 minus P. So, which is just Mn times 1, which is Mn. So that's exactly what we are looking for. So we are done at this stage for that question. We give us Mn. Good. So the second question, we want to determine C such that this expression is an Fn martingale. So that's what we're going to do here. So this is the next. Okay, so let's do that. Okay, now first of all, let's write the fact that this is a martingale, right? This is a random variable, obviously, because it's a function of Sn. Sn is a random variable, so this is a certain function. This is like g of Sn, and g is a continuous function. So measurable, so this is a random variable. So Zn is a random variable, right? Good. It's good to mention that so that we don't get confused. Good. So what we want to show, we want to define C such that the conditional expectation, right, of Z n plus 1 lambda given F n is equal to what? Zn lambda. Zn lambda, like this. So this is what we want to show. We want to show that we want C we want C such that we have this Martingale property. Now, what is Z n plus 1 lambda? So we can write it down, right? So Z n plus 1 lambda, this by definition, if we substitute that expression here, so that is Cn plus 1. So everywhere I see n, I replace with n plus 1. Lambda S n plus 1. We know already what S n plus 1 represents. So this is Cn plus 1. This will be lambda S n into lambda psi n plus 1. So if we group these two together, so you can see that the definition of lambda is this. So, and this Cn plus 1, this is Cn times C. All right, so this is C into Cn. So now if we expand, we group the two, we can see that this expression will give us C. So this will give us Z and lambda, which will be the factor Cn. If I take this factor Cn lambda to the Sn, so this one gives us Zn. This is the definition here. C to the n lambda to the Sn. That is Zn lambda. So the remaining factor will be C lambda psi n plus 1, which we can write here. Okay, we can write it in a different color, it doesn't matter. So this will be C lambda to the psi n plus 1. So now if you take all these and substitute into this expression, we have that the conditional expectation of Zn plus 1 lambda given f sub n is equal to the conditional expectation of what? Of Zn, which we can write here, Zn lambda into C lambda psi n, okay, sorry. Psi n plus 1 given f sub n. Now, this is where conditional expectation properties become interesting. This is, remember, we want C such that Zn is what? A martingale. If Zn is a martingale, the first property tells us that Zn lambda is adapted, is Fn adapted, meaning that Zn lambda is Fn measurable. If it's Fn measurable, it means that this is none, right? We can consider this to be a constant, right? So this is F This is F and measurable. So this comes from the fact that we assume that it's a martingale. So take out what is known. Obviously, even this C, we can take C out because C is a constant. It depends only on lambda. So this is deterministic. So it's deterministic. It's not a random variable. So it's deterministic. We can even take both out. So we will get C we will get C and then Z and lambda. And this is conditional expectation lambda psi n plus 1 given on, for the same reason that I mentioned above, here, this is a function of psi n plus 1. Psi n plus 1 is independent of Fn. I wrote it and I erased, so you understand what I'm talking about. So in our case, we have lambda. Is it lambda? Yeah, I think it's lambda here. So because this is independent of that, a function of the same, right? The function being measurable or continuous is measurable, will be independent of that. So the conditional expectation will just be the expectation. Okay? So that's what we are going to do, and we will substitute. We substitute that. So this is C Zn the E of lambda psi n plus 1. Right. Now we know the values taken by psi n and the properties. So similar to what we wrote before. So this will be C Zn lambda. And this will give us lambda. Okay, for -1, it will be Q. Okay, let's take 1 first. So we'll have lambda to the 1 times P plus lambda to the -1 times Q. So that is the expression of this expectation. Right. So now we know that if we assume that this is a martingale, we know that this is actually equal to Z and lambda, right? This is equal to that. But when we compute this, we get this. So now we want this C such that this equality holds, right? Good. Zn being non-zero, I'll cancel out, right? Okay, let me write it down. So this will imply that because when I will cancel out the Zn lambda on both sides, we get C into lambda P or P lambda P lambda P plus 1 by lambda Q equal to 1, right? And this is equivalent to what? This is equivalent to C into 1 by lambda, right? Factor of lambda square P plus Q equal to 1. I've just cross multiplied to reduce this sum to the same denominator, which are factor of 1 by lambda. Now to get my C, I just solve for C. So cross multiply and divide by this factor. So this is equivalent, or it implies, because what we want is C. So solving for C, we obtain that C will be lambda divided by this expression. So C is lambda divided by lambda square, sorry, lambda B square plus Q. So this is the expression of C. So at this stage, we are done. We are done. So this is our expression. This is the expression of C. Good. So, and it's a positive quantity. Lambda is positive. This positive. Oh, so it's a positive quantity. A depends on lambda. You can see. Okay, so we move to the next question. The second question, this one. It's a bit similar to what we did here above. Now we want to find the sequence AN and BN such that this MN defined this way is the Martingale with respect to the same filtration. As we did previously, we are just going to look at the Markov, to the Martingale property. The two other properties are obvious. You can do that. I'm not going to dive into that. So as we can see here, UN and VN are given. We assume that they exist. And we want to find the sequence AN and BN in terms of these two. We are going to find in terms of this. So let me copy this. This is question 2. So we are going to copy. Okay, let me copy from here. Okay, so I'll move to the next slide for the second question. Right, we are here. So I'll paste this. Okay, let's just leave it this way. And I'm also going to remove this part. Right. Okay, so here we are dealing with the second question. Yeah. Okay, so this is question 2. Oh, sorry. So you're dealing with question 2. Okay, so as we said, what we want to do here, so what we want to find is the sequence AN and BN. So we want to find these two such that capital M sub n is a martingale, right? So if it's a martingale, we know the three properties verify or satisfy by a martingale. And we assume that's given, that these two are given, right? So these two are given. So MN martingale, what does that mean? It means that for any n, Mn is Fn measurable. We are going to use that in our development. Mn is absolutely integrable, meaning that we can compute the expectation of Mn. So MM martingale means, so we are going to write that here, Mn, the sequence, greater or equal to 0 or 1, martingale. Actually, when you say martingale, is with respect to its filtration, that is M, Fn martingale. Means, of course, this is just for the martingale property, right? That the conditional expectation of Mn plus 1 given Fn is equal to M sub n. So that's what it means. Now, what does this mean? Let's write this in detail, knowing that this is equal to that, right? So this is given, Yn. Because in the expression, you see that if you write Mn plus 1, we get Yn plus 1, right? And then in that substitution, we will use this property here. Let me denote this. Let me denote that property here by star, right? For this expression. If you denote that by star, so this is what we are going to have. Okay, so since M sub n plus 1 is equal to an plus 1, yn plus 1 plus bn plus 1. n plus 1, bn plus 1. It's a sequence of real numbers, right? So that sequence is deterministic. Okay. So now if I replace the expression of yn plus 1, this one, actually not the expression directly, but I substitute that into this, is when I will substitute that I will be able to use this property star. Then this expression here above will give us conditional expectation of conditional expectation of an plus 1 an plus 1 yn plus 1 plus vn plus 1 given f n. If you use linearity of conditional expectation, if you use the linearity of the conditional expectation, we'll get the following. So here, this is equal to an plus 1, because this is deterministic. Obviously, here we have conditional expectation of yn plus 1 given fn plus bn plus 1. This is also deterministic. So when we write that, this is what we get. And now what is the expression of this? We use star. We use star. And what is star? Yn plus 1, as you can see here, given fn is yn plus vn. So we substitute that. I think that the best thing I should have done here is to say that this will be equal to via star. I can write star here on top. So this equality will give us a given star. So this is a sub n plus 1. So this is un yn plus vn. That is via star plus bn plus 1 here. And if we expand that expression, it gives us this unyn plus an plus 1 vn plus bn plus 1. And what do we want this to be equal to? Because remember that the left-hand side is this expression, mm being a martingale. So we will equate this expression with what? With mn. And what is mn? Okay, let me write it here. So this is mn. Right? So now this implies if I substitute the expression of mn, I have a sub n plus 1 uny sub n plus a sub n plus 1 vn plus bn plus 1 equal, we substitute the definition of m sub n. M sub n, as you can see here, it is an yn plus bn. So an yn plus bn. Now, if I take everything here on the right-hand side, left-hand side, and group terms, you can see that we have equality between the two, right? So if we equate the two, we will equate like terms. So we have yn here, yn there. So if we equate the two terms, what does that mean? It would just mean that this coefficient here will be equal to an, and this other coefficient here on top, sorry, the next term, this one, will be equal to bn, right? So I can write my system. So we obtain a system so the first equation of our system will be a sub n plus 1 un will be equal to an, as you can see here. And the second term here, a sub n plus 1 vn plus bn plus 1 is equal to bn. Good. So now we are going to solve this recursively. We are going to solve this recursively. I don't know how I can call this. Okay, let me call this equation 1 and this one equation 2, right? Equation 1, equation 2. Now, what do we want? We want an and bn. So that's what we want. So assuming that un and vn are given, right? And that's what we saw. So we assume that all the an's are strictly positive because we are going to divide, right? We are going to divide like this. So we assume that an is strictly greater than 0, right? For any n, strictly greater than 0. So from 1, we have that an plus 1 will be equal to an by vn. that is an plus 1 already. So now what we want is bn, right? And from 2, we have bn plus 1 is bn minus, I take this to the other side, it will be an plus 1 times vn. But that an plus 1 is what we have found here on top. So we can see that is equal to bn minus oh, that is interesting. So if I substitute this expression, you see that the vn will cancel out. So it will be bn minus an. So good. So this is equation 3, this is equation 4. So now what we are going to do, we are going to solve this recursively, as I said, because I have a sequence of an plus 1 and bn plus 1, function of an, vn, and the other one is a function of vn and an. So meaning that I have to set or fix a0. Obviously, because here we have it's like a product, an times. Now, if I want to get an plus 1, you can see that I will be multiplying all the time. So what I mean is, if I know an plus 1, the next one, which will be an plus 2, will be an plus 1 times 1 by vn plus 1. You see that? And if I substitute the expression, that will be an by vn, an by vn times vn plus 1. So you see that we cannot take an to be 0. So it has to be a non-zero value, because it will be appearing in the numerator. And in the denominator, we have products of vn. So what does that mean? That the ideal choice here for us will be to select or to choose a0 to be 1. So what we are going to do here, we are going to choose a0 equal to 1. And we can take our bn to be 0, right? Because we have like a sum or a difference. So it's not a factor. So we can take b0 equal to 0. Right. Now, recursively, if we use these two choices, we can see now that solving this recursively, let's first find our a1. So a1 will be a0 by v0, and a2 will be a1 v1, a1 v1, and this in terms of a0 will be a0 v0 v1, and that is nothing else than 1. That's the good thing about this. We could have left a0 and we take any non-zero value, but if we set it to 1, it still makes our life easy. Now we can see that it will be v0 v1. Now what will be a2? Similarly, if we compute a2 will give us a1 v1. No, sorry, what have I said? Yeah, A1, V1. Oh, I already wrote it here. So A3, so A3 will be A2, V2. So meaning that I will just multiply this by 1 by V2. So that will be 1 by V0, V1, V2. So you can see the pattern. The pattern appears already. You can see the pattern is appearing. So A k plus 1 will be the product of 1 by Vk or Vj, where j runs from 0 to k. Yeah, so that's why we can see here. So in other words, for any n strictly greater than 1, we can write that our a n will be equal to the product of 1 by Vj, where j runs from 0 to n minus 1. So that is it for an, right? With a0 equal to 1. So if we kept a0 arbitrary, we'll be multiplying this by a0 here. So we have found already the expression of this sequence an. Now, what about vn? Now that we know an, we can do the same thing here to find a recursion on for bn. So let me first frame this. So this is our, and it's interesting to get this. So anyway. So, so for our bn, with the same choice that we made here for b0, let's compute a few terms of our b, and then from there we will write the general expression. Oh, okay, so let us quickly do this. So from this expression, we can write our b1. b1 would be b0 minus a0. So b1 is b0 minus a0. We know that b0 is 0 and a1 is 1. So this will be negative 1. And what is B? B2? B2 will be B1 minus A1. And A1 is given here. So B1 is -1. So this is -1 minus A1. A1 is A0 and A0. Okay, let's write that. So this is A0 V0. Oh, sorry. Actually, it's 1 by that. So it will be this. And now if we compute B, okay, there's something that I could have done here with A0. I could have, okay, without looking at the actual value here, let me do this. Okay, let me quickly erase this. I think there's an easier formula that I can use. There's an easier formula here. So we saw that B1 from formula 4, B1 is B0 minus A0. So this is B0 minus A0. But A0 I can extract the formula from A0 here. A0 from this will be A1 V0. Because I want to avoid dividing each time. It's not too good. So B0 is 0. And A0, I can write that A0 is from this formula here. I can write that A0 is the product of A1 V0. So this is A1 V0. This is a more elegant formula. So that's for B1. Now for B2, B2 will be B1 minus A1. So this is B1 minus A1. So I will do the same thing here. I will extract the formula here. A1 will be the product of A2 V1. But our B1, I will use this value, right? So that will be equal to negative A1 V0 minus, so this is B1 and A1 is A2 V1. A2 V1, you see the pattern is coming now. And I can write this as, this B2, I can write B2 as negative A1 V0 plus A2 V1. Like this. And Okay, I will do the last one and I will write the pattern. So now if I write B3, B3 by definition from formula equation 4, B3 will be B2 minus A2. B2 minus A2, which will give us B2, this is the expression of B2. So that's negative A1 V0 plus A2 V1 minus A2 from this expression. I can write A2 here, A2 from this A2 here in the numerator will be the product of A3V2. A3V2, so which is negative. Now I can write the sum. So we have A1 V0 plus A2V1 plus A3V2. So now we can see the pattern. We have a sum of the product, right, of course, negative, sum of the product, a subscript of a term that is one step ahead of the subscript of V. You can see that here we have 1, and then we have 1 minus 0, the next one. We have 2, 2 minus 1 is 1, 3, 3 minus, so we can write that as a sum. So I can already conclude here that if I write bk plus 1, bk plus 1 here will be negative, a summation. Summation here. Okay, let me move to the next slide. Right. So I can see that for any k, okay, for an arbitrary k, okay. So for k fixed, bk plus 1 can be written as negative a certain sum on j, right? So there's negative here in front. You can see that I will have the product of a, of course, ak, v, k minus 1, because the difference of subscript is 1, right? AK has one step ahead of the subscript of VK. So that's exactly what we have here. Now let's look at the range of our K. K start from 1, right? I mean, oh, sorry, this should be J. This should be J. So this should be J. So this is AJ, J minus 1. So J start from 1. So this is 3. So I will reach 3, right? In terms of A. So it's 3 here. The highest subscript will be 3. We saw that for the case of 2 here, the highest will be 2, right? Even here, B sub 1, the highest value of A subscript, the subscript of A is exactly the subscript of B. So if it's K plus 1, it will go to K plus 1 here. Right, so this is the formula. So therefore, we can write a similar formula as this one. So for any n, Bn, now I'm going to reduce that by 1. So Bn will be negative the summation J running from 1 up to n, right? Whatever is here is there. And then we have AJVJ minus 1. Does that work? Let's see. If I take B equal to 1, B equal to 1, J just takes one value, negative A1 V0. Negative A1 V0. Okay, so it works, right? It works. So this will be for B strictly greater than 1. We have that for B strictly greater than 1. When, sorry, for n greater than 1. If I take n equal to 0, we have B0. Yeah, with B0 equal to 0. So that's what we chose to get this. So we have 0 here. Okay, so I think we are done with the question, and I think this ends, right? This ends our tutorial. I hope it was not too long. I did not even check the time. It was so absorbing that I did not check the time. Okay, let me just frame it like this. Because this thing is taking time, particularly when you want to go into the details, explaining the nitty-gritty. So you have to go into the details and write that. Okay, dear student, thank you for your kind attention. We are going to stop here. At least you understand the procedure. I think I solved all the, yeah, that is it. Okay, so thank you so much for your kind attention. I think it has taken us almost 1 hour, 30 minutes. So I was not expecting it would be this long, right? Particularly with the detail, you have to explain everything in detail. So I hope you will enjoy this. Please don't forget to like, so that by liking, you will be sharing this knowledge. Mathematics is not easy, so people need to learn. We have to expose more people to mathematics. Please make sure you watch this video again and again. Make sure also you understand the nitty-gritty, the details of conditional expectation, proving that something is a martingales, manipulating conditions. And that is it. So see you in the next video, which will not be today, maybe from tomorrow, or maybe later today, right? It's becoming more and more interesting because now it's a bit easier for me to post. It was a bit difficult, but now I'll be able to record more videos. So stay tuned and see you later. God bless you. Bye-bye.